When the James Webb Space Telescope finally peered into the farthest reaches of the cosmos, humanity held its breath. What it saw would forever change how we understand the universe. Webb had done what no other telescope could. It captured light that had traveled for more than 13 billion years. Light emitted by the very first stars and galaxies that formed shortly after the Big Bang. For the first time, we weren't just imagining the early universe, we were looking right at it. But when those first images came in, astronomers realized something was wrong. The universe. Webb showed us didn't look like the quiet, sparse, slowly forming cosmos that our models had predicted. Instead of a few scattered infant galaxies, faintly glowing in the dark, Webb revealed a vibrant, bustling early universe, packed with galaxies that were far too bright, far too massive, and filled with black holes that were impossibly large for their age. It shouldn't have been possible. And yet, there it was. Data so shocking that scientists began whispering what had once been unthinkable. Our cosmological model might be wrong. For months, the phrase echoed across universities, research centers, and late-night conference calls, a crisis in cosmology. But what if that crisis is about to unravel? What if one single object, a black hole so extreme it appears to defy the laws of physics, could hold the key to explaining everything? That object is LID 568, a black hole that doesn't just bend light and space, it breaks one of the most fundamental limits of physics itself, the Eddington Limit. And if what we're seeing is real, it could rewrite the story of how galaxies, black holes, and even the universe itself came to be. The first problem, the universe, grew too fast. It takes time to cook up a galaxy. Stars don't just appear overnight. Interstellar gas and dust drift through the void, slowly gathering under gravity's pull. Over millions of years, that gas compresses until the pressure ignites nuclear fusion, and a star is born. Those stars then live, die, and explode, spreading new elements into space. The seeds for the next generation of stars. That cycle repeats endlessly, but it's not quick. It takes billions of years for a galaxy like our Milky Way to fully form, which is why what Webb saw made absolutely no sense. The telescope was showing fully formed, massive galaxies that existed just 500 to 700 million years after the Big Bang. Galaxies that looked mature, structured, and packed with light. According to our best models, there simply hadn't been enough time for that much structure to emerge. Something wasn't adding up. The galaxies that were too bright. Part of the problem was brightness. The galaxies Webb detected were too luminous. Their glows suggested that each one was packed with far more stars than should have been possible at that stage of cosmic history. To produce that much light, these galaxies would have needed to form stars at an almost absurd rate. Hundreds, perhaps thousands of times faster than galaxies form stars today. And that defied every known model of cosmic evolution. But then, scientists at the University of Texas began to suspect something else was going on. Maybe these galaxies weren't as full of stars as they appeared. Maybe the brightness was coming from something else entirely. Something much darker. When black holes pretend to be. Stars' black holes don't shine, but the material falling into them does. When gas spirals into a black hole, it forms a glowing disk of superheated plasma around the event horizon, called an accretion disk. The friction in this disk releases incredible amounts of light, often outshining the entire galaxy around it. The researchers proposed that what Webb was seeing wasn't light from billions of newborn stars, but from massive black holes at the centers of those galaxies, devouring matter at breakneck speed. Once that idea was factored into the models, everything started to make sense. If these black holes were indeed consuming matter rapidly, the excess light from their accretion disks could explain why those galaxies appeared so bright. Suddenly, the early universe wasn't filled with impossible galaxies. It was filled with galaxies that had hungry black holes in their hearts. And once that correction was applied, the models fell neatly back into place. Problem solved. At least, partially. Because while the galaxies now made sense, the black holes themselves became the new mystery. The black holes. That break time. Small black holes, called stellar black holes, are relatively easy to understand. When a massive star reaches the end of its life, it collapses under its own gravity, compressing into an incredibly dense singularity. These black holes usually weigh anywhere from a few to 100 times the mass of our Sun. Given the time between the Big Bang and the moment Webb captured those galaxies, stellar black holes could absolutely exist. They had time to form. But the black holes that Webb was detecting weren't small. They were supermassive, weighing hundreds of millions, even billions of solar masses. And that was the real paradox. There simply hadn't been enough time since the dawn of the universe for stellar black holes to grow that large. Not if they were obeying the Eddington Limit. The Eddington Limit. Nature's speed cap. In 1920, English astronomer Sir Arthur Eddington proposed a fundamental rule of astrophysics, a kind of speed limit on how fast objects like stars and black holes can grow. Eddington realized that as matter falls into a dense object, it releases energy in the form of light. And light, surprisingly, pushes back. Every photon carries a tiny bit of momentum. Normally, that push is minuscule, but if enough photons are being released, their outward pressure can counteract gravity itself. For stars, this creates a delicate balance. If they shine too brightly, the outward radiation pressure overwhelms gravity, and the star can literally blow itself apart. That balance point, where the inward pull of gravity equals the outward push of radiation, is the Eddington Limit. Even black holes must obey it. Their accretion disks, glowing with extreme brightness, generate enormous radiation pressure. Once the accretion rate pushes the brightness past the limit, radiation pressure begins blowing material away faster than gravity can pull it in. In other words, once you hit the Eddington Limit, you can't feed a black hole any faster. The growth problem. Now, here's the issue. Even if a stellar black hole were feeding constantly, right at the edge of the Eddington Limit, it would take hundreds of millions to billions of years to grow into a supermassive black hole. But the black holes Webb was seeing had already reached those colossal sizes in just a few 100 million years after the Big Bang. That shouldn't be possible. And yet, there they were. Simulations confirmed this paradox. You could theoretically grow a small black hole into a supermassive one quickly, but only if it somehow fed non-stop at near or above the Eddington Limit for its entire life. In reality, that's not how black holes behave. They often run out of nearby gas or go dormant for millions of years before finding new material to devour. So, what were we missing? The case of the missing black holes. If supermassive black holes evolved from stellar ones, there should be plenty of intermediate black holes out there, halfway points between small and large. But strangely, the universe doesn't seem to have many. We find stellar black holes in abundance, tens of millions in our galaxy alone. And we find supermassive black holes at the centers of nearly every large galaxy. But those middle-sized ones, called intermediate mass black holes, are almost completely missing. Only a handful of possible candidates exist, and none are confirmed. It's as if nature skipped a step. This absence has fueled a controversial theory. What if supermassive black holes weren't grown at all? What if they were born massive, directly from collapsing gas clouds in the early universe without ever being stars in the first place? The direct collapse. Hypothesis: in the early universe, everything was much denser, galaxies closer, gas clouds thicker, and gravity stronger over short distances. Under those conditions, it's possible that enormous clouds of pristine hydrogen gas could collapse directly into black holes, bypassing the star stage entirely. This idea is called the direct collapse model. If true, it would explain how such enormous black holes appeared so early. They didn't grow into supermassive giants. They started that way. There's even some evidence to suggest this might have happened. But the data is still uncertain, and the idea remains controversial. And just when scientists were starting to lean toward that explanation, something extraordinary appeared. A discovery so extreme that it pushed the debate in the opposite direction again. That discovery was L. ID 568. The black hole that shouldn't exist. LID 568 is a distant black hole located between 12.1 and 12.3 billion light-years away. It's so far that its light has been stretched or redshifted by the expansion of the universe, making it invisible in normal wavelengths. Even the mighty Hubble telescope couldn't detect it. It took a combination of the Chandra X-ray Observatory, the Cosmos Legacy Survey, and the unparalleled resolution of the James Webb Space Telescope to spot it. And when they finally did, they found something astonishing. The galaxy surrounding LID 568 appears as a faint red dot, barely visible. But the X-ray emissions coming from its center told a shocking story. This black hole was actively devouring matter at a rate that seemed to violate the laws of physics. It wasn't just feeding fast, it was feeding 40 times faster than the Eddington Limit should allow. That's not a small breach. It's an outright rebellion against one of the universe's most fundamental rules. How to break the Eddington Limit. So how is LID 568 doing it? How can it eat faster than physics should allow? As it turns out, breaking the Eddington Limit is theoretically possible, but only under special conditions, and usually for short bursts. One trick lies in jets, massive beams of plasma that black holes can shoot out from their poles. If most of the radiation is being funneled out in one direction, it doesn't push against infalling material from other angles, allowing the black hole to continue feeding freely. Another possibility involves geometry. If the accretion disk is thicker or clumpier than usual, some regions may shield others from radiation pressure, again letting matter fall in faster than it should. And then there's the over-eager Diner model. For brief periods, a black hole can gulp down matter faster than it can radiate it away. It might pay for it later, expelling much of that matter in massive outflows. But during that short window, it can temporarily exceed the Eddington Limit. If this is what LID 568 is doing, it could explain how early black holes ballooned to supermassive sizes so quickly. And that means we might finally have an answer to the mystery that has haunted cosmology since Webb began its watch. A universe, still full of questions. But even as one question seems to find an answer, others rise in its place. If LID 568 is proof that black holes can feed far faster than expected, then maybe we don't need the direct collapse model at all. Maybe those supermassive black holes we see at the dawn of time weren't born large. Maybe they just broke the rules long enough to get there. But then, where are the missing intermediate black holes? And why do we still see so many galaxies packed so tightly together, glowing so brightly, when our models still suggest there should be fewer? Every discovery Webb delivers seems to solve one riddle, only to reveal three more behind it. Black holes, it seems, guard their secrets fiercely. They shape galaxies, sculpt the flow of matter, and dictate the fate of entire star systems. Yet they remain the most mysterious objects in the universe. And even the most powerful telescope ever built has only begun to scratch the surface. The lesson of LID 568. LID 568 may be just one faint speck of light in the vast cosmic darkness, but what it represents could reshape our entire understanding of cosmic evolution. It challenges our models, it questions our limits, and it reminds us that the universe still has tricks up its sleeve, ones that no equation can yet explain. In the end, perhaps the greatest mystery isn't how black holes grow, but how much we still have left to learn. After all, if there's one rule the cosmos has taught us time and again, it's that no limit is absolute, not even Eddington's. Because every time we think we've found the edge of knowledge, something like LID 568 appears, quietly breaking the rules, daring us to look deeper, think harder, and imagine further. And as long as we keep looking, as long as we keep questioning, the universe will keep revealing itself, one impossible discovery at a time.